we used an experimental setup such as this, where we had 2 water bottles as supports, and we had 2 charged pieces of tape. We had charged them with a U-tape method, and we placed 1 tape as a bridge between the 2 water bottles with some slack, and then we brought the other tape close to it until the top tape was floating in equilibrium. It was not moving. And to find the charge on the top piece of tape, or both pieces of tape, we used 2 models. The first model was as a point particle, and the second model was as a line of charges. And they both had different results. For both of the models, we needed to use a few physical principles. The first one is Newton's second law. The net force on an object is its change in momentum, or on a system is its change in momentum over change in time. And of course, the system we're looking at, which we define as the top tape, was not moving at the point of our analysis. And the other principle is Coulomb's law, which states that the force acting on a charged particle is 1 over 4 pi epsilon the force from another charged particle times the charge of the first particle times the charge of the second particle over the distance between them squared, and then r is pointing from the source particle to the particle we're observing. And now for the first method, where we treated the tapes as point charges, we had to make some assumptions. The first assumption was that each tape has the same net charge. We can reasonably make this assumption because we use the same method to charge the tapes. And each tape is a point charge is our second assumption. And this one could cause some difference between other models. The system we define as the top tape, and the surroundings is everything else. The bottom, the supports, water bottles, and our measurements, we found that at equilibrium, the distance between the tapes was 1.5 centimeters, or 0.015 meters. And we also measured that the length of tape that we had was 20 centimeters times the mass per length measurement of 1 gram per meter. We found that the tape we used was 0.0002 kilograms. Now, assuming that all the gravity is concentrated onto one point, we find that the force of gravity is mg, which is the mass we found earlier, times the gravitational constant, which is 0.00196 downwards. And from Newton's second law, the electric force, which is acting upwards, we are assuming because we're treating it as point particles, equals the negative force of gravity. And with this, we can use Coulomb's law to isolate the charge, because we treat both tapes as having the same charge. So it would be q squared instead of q1 times q2. And we find that it is the square root of the gravitational force times 0.015 meters squared. Sorry, the magnitude of the gravitational force divided by Coulomb's constant, which is 7 times 10 to the negative 9th coulombs. And this is the code, the programming to find this. R over R mag would be our R hat, so we just added it to the beginning. And it's just a way to use Coulomb's law. Except this does describe the field, so you'd multiply it by another q for the force. For the second method, we modeled it as a line of charges. Similar assumptions, except that each tape is treated as an evenly distributed line of charge. For our code, we first describe a line of charges. We create it, n equals 100 is what we used, so it's not exactly correct, but it's a good approximation. And for this, we iterate over each of the charged particles we created, evenly charged as the line, and we iterate them and we create an electric field force vector. However, using the charge we found from the point particle model, we find that the magnitude of the electric force is much less than the gravitational force. With some trial and error to get the electric force and the gravitational force approximately equal, as it should be in equilibrium, we find that the line of charges had a much less of a distributed charge than the point charge model. And the line of charges model is most likely more accurate because a line of tape is it's more similar to a line of charges than a point particle, but they're both making a lot of assumptions. So we get a lot closer with the line of charges model, but not quite exactly accurate. Now, what if electrons are positively charged and protons are negatively charged? Nothing would happen. Nothing different would change about our experiment because the tapes are similarly charged, so they'd still repel, and the electric force would have the same magnitude. So nothing would actually change. So in summation, different models can get different results, and the more you have to be careful about which model you choose because you can get very different results. Thank you.